Let me officially open this session and welcome all the participants and all the speakers. So I am Rachid Cherkaoui. I am with the Swiss Federal Institute of Technology in Lausanne. I'm very pleased to chair this session. The topic is distribution system monitoring, operation and control. So without losing time, I will start right now introducing the first paper. The title is Nonconvex Lifted Unbalanced Branch Flow Model, Derivation, Implementation, and Experiments. It will be presented by Mr. Frederik Geth. He is a research scientist working with the CHIRO in Newcastle in the Energy Systems Program. He is a power system engineer and he obtained a PhD from the University of Leuven in Belgium in 2014. His research focus is applications of optimization models in distribution network operation, including unbalanced state estimation and optimal control of battery storage system. So, Frederik, the floor is yours.
Thank you, Rashid. Hi, everybody. I hope you can hear me clearly. So the work I will present today was done in collaboration with my former team in Belgium, so specifically Sander Claeys and Geert Deconinck, who are at KU Leuven, Energyville. So my talk is structured based on the title. So first I will explain what I mean with non-convex lifted unbalanced branch flow model. Then I will go onwards to the derivation of some new features we developed. Then talk about the implementation of this model in software. And finally, I will illustrate some numerical experiments. So the basis of this work is actually a former paper of PSCC. It was presented in 2014 by Gan and Lowe. So very quickly, a summary of this paper is that they start with the unbalanced power flow physics, so as used in unbalanced power flow simulation or optimization. Next, Gan and Lowe derived an equivalent rank 1 constraint optimization model through application of lifting and reformulation techniques. They also clearly stated that this already implies a slight relaxation of the original problem, which doesn't cause any problems for radial networks. So that's fine for most distribution contexts. Finally, they dropped the rank constraints to end up with a semi-definite programming model for unbalanced branch flow. And then they use this to give to a semi-definite programming solver. So the rank 1 constraint branch flow model formulation is still non-convex because of the rank constraint. And the main question that I will try to answer today is, can we also give that to an optimization solver directly? So taking a step back, giving you a bit of background about unbalanced optimal power flow. So in unbalanced optimal power flow, we model the phases of the network explicitly. We don't assume that everything is balanced. So a generalized version of a branch then includes a series impedance and shunt admittances matrices, which have as many values as you have conductors in your system. So I will use matrix notation in bold to indicate matrix variables or vector variables. So UI is the vector composed of the 3 phase voltages, and ILij is the vector composed of the 3 currents flowing through branch L from I to J. So we can already directly describe some vector equations, for example, that the total current flowing into the branch divides over the series current, over the series impedance and the shunt admittance. This is also very convenient to define Ohm's law, and more in general, the circuit laws, which we need to represent the behavior of this system mathematically. So you see that in those vector variables, the modeling looks very recognizable. But of course now multiplying the impedance and the current is a matrix vector product. Something that is slightly less obvious is how to deal with complex power. So power is still the product of current and voltage conjugate, but the correct generalization is actually the voltage vector times the conjugate transpose of the current vector. So it's an outer product. So it actually generates a 3x3 matrix, for example, when both U and I are 3x1 vectors. For ease of the derivation, I actually define two separate complex power quantities. So one is the total complex power flow through the branch. So that includes the parts through the series and the shunt element. And then there's also a series power flow variable, which is the product of the voltage vector with the series current. So it tells you how much power is flowing through the series element in the pi model branch. As proposed by Gannon law, we introduce a new variable to represent the voltages as well. So this is defined as the voltage vector times its own complex conjugate transpose. So it's Hermitian adjoint. So this kind of a process where you do the outer product of a vector with its own transpose with its own conjugate, generates a Hermitian matrix which has a bunch of symmetries which can be exploited numerically. We do the same thing with the series current. So this, in this case, indicated with the symbol L, where we multiply the series current with its own conjugate transpose. And it again generates a Hermitian matrix. So one of the big steps that Geth and Lowe took in their paper was to develop a vector stacking technique to help formulate a positive semi-indefinite rank constraint model. So the definition of these WL variables allows us to substitute to develop a block matrix M, which is composed of WL and the series power. And Geth and Lowe showed that we can also get rid of the original voltage and current variables. We can eliminate them, but still, given some conditions, be able to recover them after solving the optimization problem. And the main condition is that this matrix M is rank 1 at the end of the solution process. Putting everything together, this is the feasible set that they derived. And yeah, in general, this actually works for any size of impedance or admittance matrices. So it works for a single conductor, but it also works for 3 and 4 conductors and more. So showing you an example about the balanced case, so where the vector is length 1. We derive this M matrix as well. And in the literature, you will see that also people use an alternative form of this constraint, which is a quadratic one involving the same variables. And if the original matrix is positive semi-definite and rank 1, this means that this quadratic form is met inequality, and the other way around, we can go back as well. The question here is, how do we generalize this to vectors with a length longer than 1? So when M is a matrix of 4x4 or 6x6. So the next step then is to, the approach I took was to multiply the complex power matrix with its own conjugate as well. And after some algebraic manipulation, we recognize that there's a scalar hiding there, which we can cast as a trace of this L variable we introduced. We also can extract the W variable we introduced. So we now end up in an expression between S, W, and L. We can also do the same thing but multiply on the left. And again, we obtain an expression between S, W, and L. If you scalarize this, expand this, you end up with a set of equations which looks like this, which is quite tedious to actually implement. So I'll come back later how we did that. So we now have a new feasible set. We have still the original equations representing the losses in the branch and the voltage drop over the line, but instead of these PSD matrix and rank constraints, we now have two nonlinear matrix equalities, which we will use to replace those. So this is what most of the paper is about. So I show that this polynomial reformulation is equivalent to the rank constraint positive rank constraint semi-definite programming problem under some easy to satisfy conditions. This polynomial structure generates some new second order cone relaxations, but they are they don't represent an improvement on what we already knew based on the 2x2 principal minor relaxation. In the rest of the presentation, I will talk about some of the key arguments I developed. So, knowing that the rank of a matrix is maintained, if you multiply this a matrix with its own conjugate on the left or the right, these two equations together actually tell us that the rank of S, W, and L will always be equal. So we can use this feature to propagate rank from one bus through a branch to the next bus. So as long as the network is connected, the rank of all of these variables will be the same. That means if we somewhere have a rank 1 anchoring point, that this propagates through the whole network. And then again, the results from Gan and Low apply. So as long as we have rank one variable somewhere, we know that everything is going to be rank 1 and that we can map it to a physical solution in the power voltage or current voltage variable space. Up to the next part, I will talk about the implementation. So this is actually quite a challenging thing because few optimization modeling languages or solvers have native support for complex matrix variables and nonlinear vector or matrix constraints. Typically, they operate in the reals and with just scalar equations. This implementation was developed on top of an open source toolbox power models distribution, which is itself built upon Julia for Mathematical Programming, or JUMP. And we are using IPOpt as a nonlinear solver. And we use the built-in OpenDSS reader to run test cases. So on the right here on my screen is the set of equations we actually implemented, but there's a whole bunch of steps to get to the point where you can actually give it to the solver. I refer to the paper for the details. To end with some numerical results. So they were quite challenging to generate, which I will talk about. So we tested up to a system of 203 phase buses, which is a reduced version of the LV test case, one of the IEEE benchmarks for power flow, but we extended it slightly for OPF. And we make sure to validate the feasibility with respect to OpenDSS. So in red, I indicated the formulation that is derived in the paper, and we compared it with some other formulations for unbalanced optimal power flow, namely the AC polar and rectangular forms for the unbalanced representation.
2 minutes.
Yep. So we saw that the objective values and the optimized decisions were actually consistent with those formulations. But I also noted a high amount of numerical challenges. The optimization model was very sensitive to the choice of power base in the non-dimensionalization. We had to take care not to initialize certain variables in 0 because that would lead to bad convergence. Nevertheless, the amount of interior point iterations that solver had to do was still much, much higher than any of the competing formulations. So yeah, there's still lots of interesting science to do in that direction you want to apply this to bigger networks with burst scaling. So in conclusion, we developed a lifted but non-convex branch flow model for unbalanced modeling of networks. It's exact for radial grids. It extends the nonlinear disk flow equations to the unbalanced case. It's defined in the same variable space as proposed by Gann and Lowe, so the lifted semi-definite relaxation of the branch flow model. The technique works. There's still remaining numerical challenges. And the work also underlines the need for the development of a benchmark library for unbalanced optimal power flow, similar to what, for example, PGLib has achieved. So that was my talk. I give special thanks to David Folks and Carlton Coffrin, and then I'm open for questions now or later when you contact me through email. Thank you.
Okay, thank you very much for your presentation. So now let's move to the question and comments. There is a question in the Q&A. Do you see the Q&A question?
Yeah.
Q&A. I can, or maybe I can tell you the question. Do you see?
So yeah, I can see it. Yeah.
Okay.
So it was.
Can you read the question? What about this?
Yeah.
The solve time
Yeah.
for
Yeah.
data?
Yeah, so in terms of calculation time, this was not competitive with the AC polar or rectangular power flow formulations, mainly due to worse convergence and yeah, a larger amount of interior point iterations being required. The networks still were solving pretty quickly in seconds, but arguably this formulation was significantly worse than AC polar or rectangular. Or even a semi-definite relaxation. Yeah.
Okay, thanks. Any other question? Yeah, there is another question. Can you read it?
Yep. So I can let me first repeat the question. So Dan Molzan asks, can I expand on the numerical challenges? He states that Stephen Lowe has shown that the branch flow model typically has superior numerical performance for balanced cases compared to bus injection models. So this is surprising. Yeah, that's that's a very good question. So the challenge here is that you have a lot of equations, a lot of nonlinear equalities in your model. So let's go back. I guess here. So these two sets of polynomial equations we are adding each generate 9 scalar equality constraints, which look like this. It's only 9, not 18, because of the symmetries. But yeah, so you end up with 2 times 9 nonlinear constraints involving quite a few variables, as you see depicted here. So I think it's mainly to do with how the amount of constraints scales with the dimensionality of your impedance matrices.
Okay, so maybe still very quick question. No, there is no any other questions, so we can stop here with your presentation. So thank you very much, Frederik, for